To optimize a function, or to sketch its graph, we use the following important results. If f prime is positive on an interval, f is increasing there. And also, if f prime is negative on an interval, then f is decreasing there. Other calculus courses don't go deeper. They don't ask anymore why these statements are true. However, in our case, we want to understand better why the world works the way it does. So why are those statements true? The answer lies with the mean value theorem of section 3.2. To arrive at the mean value theorem, we first need Rolle's theorem, named after a French mathematician who is dead. So it goes this way. Suppose f is continuous on a closed interval ab, differentiable on an open interval ab, and f of a is equal to f of b. The last condition means that the points on the graph corresponding to a and b are at the same level because their y-coordinates are equal, and because those y-coordinates are the function values f of a and f of b. Okay, what's the conclusion? It's that there is then some number c inside ab, inside that open interval, so meaning c is strictly between a and b, such that f prime of c is equal to 0. The geometric interpretation is that c is a critical number of the first kind, meaning that the tangent line there is horizontal. Such a c is not unique. As you can see from the figure, there are 2 points labeled C1 and C2 for their x-coordinates, where the tangent lines in red, or tangent segments, are both horizontal. So, why is this true? Let us consider 3 various cases. Case number 1. So, there's an illustration on the right side. The points on the graph in purple for x equal to a and b are at the same level. Suppose that there is another point on the graph which is higher than the endpoints at a and b. So in other words, suppose there's some number d inside a and b, that open interval, such that f of d is strictly larger than f of a, and hence also larger than f of b. We're not saying that the entire graph is going to be above this red segment. It could be, as in this original illustration, there's a part of the graph that's above the red segment, not excluding the possibility that there could also be a part of the graph that's below the red segment. Okay. Well, because from the first condition, f is continuous on the closed interval ab, then according to the extreme value theorem, our function f, it should have an absolute maximum on the closed interval ab. But of course, it's also true that f would have an absolute minimum. But for the proof of Rolle's theorem, for this particular case, the fact that f has an absolute maximum is exactly what I need. Anyway, this is a sit back, relax, and enjoy kind of thing as I prove Rolle's theorem, and you don't have to replicate this, so all that's expected of you is to be able to follow the proof and try to understand as you go along. Alright, so f is an absolute maximum. Now, because there already is a point on the graph that's higher than f of a and f of b, therefore this absolute maximum, alright, would have to occur at some number c, strictly between a and b. We know how from the extreme value theorem, the absolute extrema can occur at the endpoints. So in this case, the absolute maximum could potentially occur at a and b. However, that ship has sailed. The absolute maximum cannot be at a and b because there is some other point on the graph which is higher than the points at a and b. So therefore, the absolute maximum would have to be at some number c which is strictly between a and b. All right, but therefore that means f has a local maximum at C. You can see that clearly from the figure and from one of the results earlier stated. It means that C is a critical number. Remember how a local extremum can only occur at a critical number? So if f has a local maximum at C, then C is a critical number. It's either type 1 or type 2. And that's where we then get to use the second condition of Rolle's theorem, that the function is differentiable at every number strictly between a and b. C is such a number, and therefore f prime of C exists. However, if f prime of C exists, the question now is, what kind of critical number is it? Is it a type 1 critical number or a type 2 critical number? Well, then it can't be a type 2 critical number where f prime of C does not exist, because we just argued f prime of C exists because f is differentiable at number C. But then that only leaves the possibility, one possibility, C is a type 1 critical number. In other words, f prime of C is equal to 0, and that's what we're trying to prove, that there is some number C between A and B such that f prime of C is equal to 0. And so from the illustration here, such a number C is where you have a local maximum. Okay, second case. Suppose there is a number D between A and B such that f of D is lower than the common value of f of A and f of B. So there's a point that's below. Now, how we proceed with the proof can be done very similarly to what we did in case number 1. Well, f is still continuous in AB, and so accordingly, f would have an absolute minimum this time. And this absolute minimum cannot occur at A and B because there is a lower point. So then the absolute minimum would have to occur at some number C, strictly between A and B, where you have actually a local minimum, same story. And because the function would have to be differentiable there, then f prime of C is equal to 0. Similar argument as case number 1. In fact, if you go look at the proof of Rolle's theorem in the book, that's how they proceed. But instead, let me present an alternative. All right. Instead, let g of x be the negation, negative of f of x. Negation is a weird adjective. Let's just say negative f of x. All right. And then note that because there is, well, okay, g is continuous on AB because g and f are just negatives of each other and therefore differentiable in AB, and because f of A is equal to f of B and g is merely the negative of f, then consequently g of A would still be equal to g of B. And furthermore, if f of D is less than f of A, then that means g of D is greater than g of A. Like if you multiply this inequality by a negative symbol, so negative f of D would be g of D, negative f of A would be g of A, so therefore g of D would be strictly greater than g of A. Now what am I getting at? What I'm getting at is that the function g now satisfies all the conditions prescribed in case 1 for the function f. And therefore, the conclusion we drew regarding the function f from case 1 should also apply to function g. So, in other words, there is some number c in AB such that g prime of c is equal to 0, because the function g satisfies the conditions of case number 1. But g and f are negatives of each other, so therefore their derivatives are also going to be negatives of each other. In particular, g prime of c is negative f prime of c. Hey, but if g prime of c is 0, what does that imply? That f prime of c is also 0, and so we end up with the same conclusion. Okay, what's the last case? This function whose graph is shown here, which my house is hovering over, actually satisfies both case numbers 1 and 2. So essentially, we have assumed, suppose there's a point on the graph that's higher than f of a and f of b, and there's a point on the graph that's lower than f of a and f of b. Of course, a graph could have both such points, somebody higher and somebody lower. What if nobody is higher nor lower than the two endpoints? The only way that could happen is if, well, the graph would be a horizontal segment. In other words, f of x is equal to f of a. Like, it doesn't matter what x is, how it's chosen between a and b. The output, the y coordinate, would be the same as at a anyway. All right, but then in that case, if f is constant on that closed interval, then the derivative is 0. All right, what are we trying to show? That it's possible to select a number between a and b where the derivative is 0. But hey, here, the derivative is 0 for any number between a and b. And so therefore, this hypothetical number c, under the third case, can in fact be taken as any number between a and b. Alright, so yay, Rolle's theorem is true. Now let's apply Rolle's theorem to various examples. For your convenience, the statement of Rolle's theorem is here. If f is continuous in AB, closed interval, differentiable on the open interval, and then f of a equals f of b, therefore f prime of c is 0 for some number c between a and b. Let's illustrate Rolle's theorem. Just verify that it's true for this function, x to the 4 minus 2x squared on the closed interval, negative 2, 2. Alright, well, first, if we're going to verify Rolle's theorem, let's verify that the conditions are met. So is this function continuous on negative 2, 2, that closed interval? Yeah, because f is a polynomial. Is it differentiable on the open interval negative 2, 2? Affirmative, because f is a polynomial. In fact, it's continuous and differentiable everywhere. And then lastly, are the function values at the endpoints negative 2 and 2 the same? It's a straightforward verification. F of negative 2 and f of 2 are both 8. So the conditions of Rolle's theorem are true. Now, to verify the validity of Rolle's theorem, we have to show that there is indeed a critical number of the first type. Well, in fact, it's possible to look for it exactly by starting with the derivative. F prime is 4x cubed minus 4x, factorable easily into 4x times x squared minus 1. Will this ever be 0? Yes. In fact, we easily see that f prime of c is 0 when c is either 0, 1, or negative 1. So in fact, in this case, we have, of the number c guaranteed by Rolle's theorem, we actually have 3 of them. All right. Next point, next remark, just like with any theorem, if not all the conditions are satisfied, there is no guarantee that the conclusion would follow. So as an illustration that the conditions are all important, let's consider the absolute value function. And then the interval negative 2, 2 was arbitrarily chosen. So yeah, clearly this absolute value function is continuous in this interval. It's actually continuous everywhere. And then it's easy to see that the function values at negative 2 and 2 are the same because, well, the absolute value of negative 2 and 2 are both 2. However, the differentiability condition, is it satisfied? Is the function f differentiable at all numbers between negative 2 and 2? The answer is in the negative, because we know that f, the absolute value function, is not differentiable at 0. If you look at the graph, there's a sharp turn made where x is equal to 0. So that means the conclusions of Rolle's theorem are not satisfied. There is therefore no guarantee that you have a critical number of the first type. And in fact, that's true. There is no number c between negative 2 and 2 such that f prime of c is equal to 0 because, well, okay, when x is 0, f is not differentiable. Then when x is positive, f prime is 1. Then when x is negative, so that this reduces to negative x, f prime is negative 1. So in this case, nowhere does the derivative f prime ever become 0.